this is just the same graph as before, plotted almost up to boiling, right? So even when boiling, if you take ice and put it on boiling water, as long as it's around, it's still going to float on top. So that's how big of a density difference we're talking about. The next one doesn't have the ice on it, so you can kind of see that rate of falling off faster, more clearly. Right. So the question that Bronson asked about that rate, you can see the rate more clearly. And the last one is only plotted from 0 to 10, and it doesn't have the ice on it, so you can see where that maximum lies much more closely. Okay, so that's just another figure from the book to illustrate those major points that are kind of hard to see when you have that whole overall graph on. But these are the major points I still want you to have on the graph, basically. So this one doesn't actually, these aren't plotted with that break in there on the y-axis. It's another way of looking at it. Okay, so when we add salt to water, what happens to density? I already told you that. Does it increase or decrease? It increases, right? So the salt, basically the salt's dissolving in the water, you're putting more molecules per cubic centimeters, and so it's going to be denser. And it has a much bigger effect than the temperature effect. So what this graph shows is the range of densities under normal temperatures at the surface in gray, right? Just sort of a band of those. And then it has sodium chloride concentration on the x-axis and density on the y-axis. And we see that the approximate density of seawater, right, is the difference associated with that is much greater than the density difference associated with temperature. So if we have saline layers, like a saline and a non-saline layer, they can be much more stably stratified than the stratification based on temperature. So what happens to river water when it comes into an ocean?
Over the top.
Floats on the top, right? Until it mixes enough salinity and gets even enough, and then it'll go. So all the rivers, the Amazon and Mississippi, are flowing in across the top until they mix well enough. And that's because their density is going to be somewhere in this range, and the water in the ocean is going to be somewhere here, and this is much heavier. Okay, so now we've kind of gone through these major properties of water: heats of vaporization, surface tension, all the relationship between temperature and density. And now we're going to talk about the relationship and how these vary between the properties of water and scale. And this is very important because while we operate at a scale of a couple meters, bacteria are operating at a scale of a micron, and zooplankton at perhaps a tenth of a millimeter, 100 microns. And they are experiencing their environment very differently than we are. In addition, many biological processes occur at very small spatial scales. And so they are also occurring in a different physical frame of reference than we experience on a day-to-day basis. And what we'll talk about is how these different things alter the way organisms adapt to their environment and constrain the way they've evolved to deal with their environment and interact with each other. So there's a direct biological relevance of this. The bad news is that it requires equations, and they are algebraic equations, but nonetheless equations. And so we'll get to those, and I'll try to put those in words as much as possible to guide you through those. But you know, it's pretty simple concepts. So the main thing that happens that alters this relationship between scale and the way properties of water are is that the smaller scale you get, the more important hydrogen bonding becomes. So you can just, the example here, you think of us walking through a spider web versus a fly trying to walk through the spider web. It barely affects us. The fly can't get through it. The bacterium is the same thing going through water. It is much more influenced by that hydrogen bonding because it's sort of tugging on all the other water molecules as it tries to push through. Whereas we're so big that that doesn't have an effect on us. That hydrogen bonding is actually causing the viscosity. That is how viscous that solution appears to be to those organisms. It also changes the way inertia works. So inertia is basically the tendency of a mass to keep moving. It turns out that a bacterium, because it's experiencing that tug back of hydrogen bonding, when it stops swimming, it has essentially no inertia. It just stops instantaneously, probably about a coast of micron. If you have a very large fish and it stops swimming, and I'm sure you've seen this, you know, like a pike or a fish that goes really fast, start with, and they'll just stop and they'll be gliding, right? They'll have a lot of inertia and they'll just keep going. So they're really different physical relationships.